Good morning. We are Group 1 and we will be present about our short report. My name is Chan Shiro and my teammate is Peng Zhu, Ding Yanlu, and Ding Xingyi. Now I will pass to Ding Yanlu to start her presentation.
Thank you, Chiro, and my name is Ding Lu. So, to begin with, the selected magnetic element in our project is a single long straight current carrying conductor, which is one of the most fundamental elements in magnetostatics. When a steady current flows through the conductor, a magnetic field is generated around it in the form of concentric circular field lines. The direction of this magnetic field can be determined by using the right-hand rule. According to Ampere law, the strength of the magnetic field decreases as the distance from the conductor increases. As a result, understanding this magnetic field behavior is important in electrical engineering, and it is common application in electrical wiring and power transmission system. Furthermore, these concepts serve as the fundamental for more advanced electromagnetic devices, such as transformers, inductors, and electrical machines. Overall, the single long straight current carrying conductor is a fundamental magnetic element that helps us understand the relationship between electric current and magnetic field. That's all from me, and I would like to pass to the next person.
Thank you, Yanlu. My name is Peng Zhu, and I will introduce our system design. First, the current carrying conductor is assumed infinite long and in free space. The magnetic field produces a circular field lines around the conductor. By using right-hand rule, the magnetic field is in counterclockwise direction. The current carrying conductor is along the z-axis, and the DC current is flowing through it, which produces the magnetic field. The observation point is located at radial distance r. The number of turns of a single long straight conductor is 1, and the radial distance is set to 2 millimeters. The current flow through the conductor is 5 amperes. At free space, the permeability is mu0, which is 4 pi times 10 to the power of -7. Since it is assumed to be infinite length, we can say the length L is much greater than radial distance R. Now I will pass to Xingyi.
Thank you, Zhu. Now this is my part of system simulations. For this project, I use firm finite element mathematics to simulate the magnetic field distribution around a current carrying conductor. The purpose of the simulation is to visualize how the magnetic field is generated and distributed when electric current flow through a conductor. Step 1, I created the geometry. A circular conductor was drawn at the center of the workspace to represent a copper wire carrying current. The conductor was assigned a radius of 2 mm. Next, the material properties were assigned. The conduct is upper diagram. Yeah. Next, the material properties was assigned. The conductor was assigned as copper because the copper is the good electrical conductor. The surrounding region was assigned as A. A has a relative permeability of approximate 1, which means it does not affect the magnetic field distribution. A circuit property was assigned to the conductor is the current has set to current equals to 5 and number of turns is equals to 1. This means the current of 5 ampere flow through the conductor. To represent a open magnetic domain, a large circular boundary was drawn around the conductor. This boundary ensures that the magnetic field can spill naturally into the surrounding air without being artificially limited by the simulation area. After all the parameter is defined, firm can generate the simulation result, which is below, is this. At r equals to 2 millimeter, we can get the magnetic field equals to 0.0004952 Tesla. We can observe that the strongest magnetic field occurs near the conductor and gradually decrease at the distance from the conductor increase. When smaller the distance, will stronger the magnetic field. When larger the distance, will weaker the magnetic field. This simulation shows that the strongest magnetic field occur near the conductor. The magnetic field decrease with increasing the distance. The magnetic field line form close circular loops around the conductor. Yeah, that's all from me. Next, I will passing it to the Chanchilo.
Thank you, Ding Xingqi, and I will be continue to the comparison part. Our theoretical calculation using Ampere law, which is B equals mu I over 2 pi R. The I we set at 5 ampere, distance is R equals 2 millimeter, and also sub into the formula, we get the result is B equals to 5 times 10 power of negative 4 Tesla. So compare the theoretical and the stimulation, we get that the difference is 0.96, which is a small difference between the theoretical part and the stimulation part. So the stimulation is slightly lower than the theoretical part by approximate 0.96 percentage. The similarity to the theoretical part and stimulation part are very close, but the firm result is about 99.04 of the theoretical part. Both results shows that current carrying conductor produce a magnetic field as predicted by Ampere's law. The possible reason for the variation is that the small difference between may caused by the firm mesh approximate numerical rounding and boundary condition. The theoretical calculation also assume an ideal infinite long walk conductor with firm use a finite numerical model. However, error is less than 1%, so the simulation agree well with the theoretical result. And this is the analysis of parameter change, which the magnetic field is inversely proportional to the radial distance. The magnetic field is also directly proportional to the current. Now I will continue to talk about the magnetic field, magnetic flux density vs the current. Let the radial distance fixed at r equals to 0.1 meter, and we will be seeing the graph show that a linear relationship between the current and the magnetic field. When the current is increased, the magnetic field density also increase. Now I will pass to Ding Tuo to continue the magnetic flux density vs radial distance.
Thank you, Chiro. So I will continue analysis the relationship between magnetic flux density B and radial distance R. From the data, it is observed that the graph shows an inverse relationship. So it is proof that the B is inversely proportional to R. So both radial distance and current have significant effect to the magnetic flux density. They affect the magnetic flux density by a factor of 1/5 and 5. So we can conclude that they have equally strong effect on magnitude of change in magnetic flux density, but in opposite direction. Now I will pass to Yan Lu.
Thank you to her. And in conclusion, this project demonstrated the behavior of the magnetic field around a single long straight wire. The result verified that the magnetic field depends on both the current flowing through the wire and the distance from the wire. In addition, the theoretical and firm simulation result show excellent agreement with only a 0.96% difference, demonstrates the validity of Ampere's law. Hence, the objective of this project was successfully achieved. A limitation of this study is the use of ideal assumption in the theoretical analysis. For further improvement, a more realistic conductor models and surrounding material should be considered to assess their effect on the magnetic field distribution. That's all from me. Thank you.
So this will be our reference parts, and that's all for our presentation today. Thank you.